everyone, so this is Umakan. So now I come from my lab. So I came to know that tomorrow is the IIT Bombay PhD interview for physics department. So I just want to make a video in order to convey a few important questions that have high probability to be asked in condensed matter physics sector section in the interview. So this video will be a small video, but the points are so important. So see, there will be three panels here, 2 to 3 panels, and every panel will be have 3 to 4 professors. Generally, that is the trend in IIT Bombay Physics Department. So in experimental section, the probability of getting questions about the semiconductor physics is high. Okay, so they people may asked. I have just averaging the question from previous years and from my year to this last year. So they may ask about the semiconductor, insulator, and metal. What is the difference? So if someone will give you some identical pieces of metal, semiconductor, and insulator, so then how you will distinguish them experimentally or any scientifically, how you will distinguish them? Okay, so in that case you can say something about the conductivity, Hall measurement. You can say about the photo detector application, because semiconductor will give you some electron hole pair separation, which will be not possible in insulator and in metal. So photo detector you can fabricate. So also you can study the observation spectra. Okay, that will say about the metal, insulator, and semiconductor, because metal will absorb all the radiations, but the semiconductor will absorb depending upon its band onset. So specific wavelength will be absorbed. So you will get a proper offset and onset in the observation spectra. Then they will ask about the how to get the proper band-to-band transition energy of a semiconductor, unknown semiconductor. Okay, suppose valence band maxima and conduction minima. So in that case you have to say that is observation spectroscopy or reflectance. Okay, from that you can have the band gap determination. Then there are photoluminescence is possible, but photoluminescence not always give you the band to band transition depending on the metal quality. Okay, sometimes it gives some excitonic band gap, so it will be like below conduction band minima. So that is the point. Then they may ask about Hall measurement. Hall is so important, so don't miss Hall measurement. How to perform Hall experiment experimentally? What is the factor that can be extracted from the Hall measurement? That is important. Okay, so you should be clear about the Hall measurement. Don't go to the definition like a magnetic field will be given, some electric field will be given perpendicularly, so the voltage will be developed across or perpendicular to both magnetic and electric field will be Hall voltage. That is the basic definition. But how it is working, how Lorentz force come into the picture, and what is the application, what is the vital role of this experiment in the material perspective, what is the importance of this experiment? Okay, that is my concern. Then one important question will be direct band gap, indirect band gap. Okay, how to determine a direct band gap and indirect band gap material? Okay, so what is the basic difference between the direct and indirect band gap? Like in direct band gap there will be K conserved in valency band maxima and conduction band minima, but indirect there will be no conservation of K. So you have to transit that electron to the conduction minima by a phonon assisted mode. So that is the important. But they will ask what is the importance of a direct band gap material. For LED application you need a radiative transition, so you need a direct band gap material. So what is the example of the direct band gap material? Then it will be gallium nitride, and there is a lot of material which are under direct, but indirect mostly material are indirect. Okay, like silicon, germanium, and these our material MOS2 and nickel oxide, zinc oxide, these all are indirect material. So they may ask about the give some material name which will be applicable for UV detector, UV range applications, UV photo detector, UV transistor. It will be wide band gap material like metal oxides, zinc oxide, nickel oxide, these are. Okay, so that is important. You should know the how to determine it is a UV active material or it is IR active material, it is a visible active material depending on the band gap. Then sometimes they ask from the superconductivity part. Okay, so what is the basic definition of superconductivity? Plot that rho versus T variation, and why are T equal to 0? This rho is not equal to 0. The metal should have zero resistance at the 0 Kelvin, but that generally don't occur, because some defects are there, so it will introduce some kind of resistance. that mean free path, relaxation time, and drift velocity. These three things are very important because they are all related to mobility. Okay, that part you should be clear ki how these parameters are correlated with each other and how you can control them experimentally. Okay, then one important part come in the PN junction. So they will ask you to draw the IV characteristic of the PN junction, and depending upon the IV characteristic, you have to explain what is this knee voltage, what is this reversal voltage, how temperature dependent PN. Okay, so why this is so, that is important. So suppose like IV, suppose they will give you an ohmic junction, that is linear IV. Okay, and they will give some Schottky barrier. Okay, Schottky junction, you know Schottky, like they will non-linearity. How to extract the Schottky barrier height? Okay, can you comment on the symmetric Schottky or it is a asymmetric Schottky? Basically, Schottky junction form when a metal come into contact with a semiconductor. Okay, at the interface of the metal and a semiconductor, that is MS junction, the Schottky barrier forms. So electron have to cross that barrier in order to be injected into the semiconductor. Okay, that contact resistance come into the picture. Yes, there is another thing, that is 2 probe and 4 probe method. Why this 4 probe method come into the picture after 2 probe method? So what is the importance of this 4 probe measurement? What you can extract from the 4 probe method, that is contact resistance, that is TLA method, transmission line method. Okay, so you have to fabricate device with the different length, channel length, then you have to plot resistance versus channel length, then intercept of this linear plot will give you the RC, that is contact resistance. That resistance come into the metal semiconductor interface. That is a crucial factor in the device perspective, so just keep it in mind. Okay, so then some picture come in the band diagram. They will ask about to draw the PN band diagram. Suppose they will give a 3.2 electron volt band gap and some metal like gold having the work function 5.5 electron volt, 5.6 electron volt, that range. So how to draw the band diagram at equilibrium at different temperature? Okay, one important question from the semiconductor: how to comment on the N type or P type conductivity of this metal? How to know it is a N type semiconductor or a P type semiconductor? Can you say? This is interesting. So I will say some things to explain. Like N type metal, you can do the Hall bar measurement. You can have this 6 Hall bar structure or Van der Waals structure, then you can extract the carrier conductivity N, that from where you can find out this mobility. Okay, so depending upon the charge carrier nature, you will get a negative or positive conductivity in the material. That's the only way, that is one way. Okay, but apart from that, there is other way, like you can fabricate transistors. Okay, field effect transistors, depending upon the gate voltage, or whether your positive, with your positive gate bias voltage, your source to drain current, that is IDC, is increasing or decreasing. That will save the conductivity nature of the carrier in the channel material. If you're positive, with your positive or with increasing of VG value or gate to source voltage, your IDC is increasing, that is a N type material. But with negative gate to source voltage, if your IDC is increasing, it is a N type or P type material. Okay, so that is a different part of the story, but you know, by doing Hall measurement, by doing FET fabrications, you can comment on the N type or P type nature of the material. Okay, suppose you fabricate or you got a material. Okay, you synthesize some material. How to find the stoichiometry? Suppose you are preparing a zinc. This video will be very crucial, I am saying, so don't miss any question. It will, from my experience from last 6 years, so this question will definitely ask you in any IITs, not only IIT Bombay, outside India, Europe also ask this question to the Indian student for last few years. My friends are there in PhD, so don't miss this video, it is so crucial. So, and it is going to be interesting, and I am enjoying this video. Okay, so come to the point. So if they will ask where I was lying, I was in the semiconductor FET N type P type conductivity. Yes, stoichiometry. If suppose if they will give you a zinc oxide thin film. Okay, can you comment the zinc by oxygen ratio? Okay, so you have to do the XPS. Okay, X-ray electron spectroscopy. Okay, so that XPS will say those stoichiometry, atomic percentage or ratio, how they are atomically, or atomic percentage, how the deficiency is there, from where you can find out the defect density. Okay, then one important questions always come ki, that you know ki whenever you are preparing some material, you have to do the characterization. So first characterization, that is the crystallinity nature of the material, is come under XRD, X-ray diffraction, which under Bragg's law, n lambda equal to d sin theta. how this n lambda equal to 2d sin theta is get implemented, and what are the important questions always come from the XRD. I have prepared a video 2 years back in my channel. You can see a specific video which tells about the various important question can be asked in XRD. That is most important part of the interview. XRD must, because it comes in the MSc syllabus. That's why they people always prefer to ask these XRD questions. So I will not say about XRD because you know from my previous video there are a lot of questions provided. But after doing XRD, how to do the surface characterization, like surface roughness, a thin film having roughness in nanometer scale, okay, or basically nanometer scale only, in tens of nanometer, hundreds of nanometer. So from atomic force microscopy you can have this idea. So do some basic research how you can characterize this material, and every characterization leads to some information, scientific information. So what is that? That is important. Okay. So that is the case, but yes, there is another question like from that Croney-Penny model that always asks what is effective mass, what is the real definition of effective mass, and how it is affecting the properties of the material. Okay, how this tight binding model come into the picture, how band dispersion come into the picture, what is the factor that can affect your band diagram, physical factor like temperature, pressure, like strain, everything can affect the band diagram. And if your band diagram get disturbed, then every property, optical and electrical property of the material can be disturbed. See, one simple thing, if you have a semiconductor, okay, if you have material, then in the two way you can characterize it. Okay, one way is the optically, second is the electrically. Okay, so it depends upon your interest which probe you will use, or which probe you are interested in. Optically you want to stimulate the material and get the response, or electrically. Okay, these two channels are there. So go through the interview and try to convince them, but they people will be happy if you answer in experimental way. Okay, that's why I'm always saying, so just go beyond of your syllabus and think something how this device is fabricated, like a solar cell, how it is fabricated, highest battery like sodium ion battery, potassium ion battery come into picture now. So how this battery is working, how a FET is working, how a MOSFET is working, how a MOS capacitor is working, simple MOS capacitor, there are a lot of physics. So just think about this. There is a lot of video in the YouTube, like NPTEL videos from IIC professors, IIT Bombay professor, IIT Delhi. Various IITs have its own NPTEL classes. So just go through them and just think that can be asked. And IIT interview and IIC interview will be fun. So just enjoy the interview and try to answer them scientifically, whatever you are thinking. And these are the important questions. Don't miss them. So you can just note from my video what are the questions and answers. If you have any doubts, or you know the answer, you want to know the answer, then you can write me mail or comment. I can provide them. So I just come from my lab. I think this is a important it is going to be an important video, because I from the friend I came to know that the interview will be there tomorrow. So I just provide a video, and this video will be applicable for interview in condensed matter physics, experimental or theory, but in all IITs, all institutions and beyond India also. So just go through it, and thank you so much for watching my video, and thank you so much for your support and love. Thank you.